Okay, so we've looked at several modulation schemes up to now. We looked at several types of AM, and we looked at angle modulation as well. And we saw three major things for each one of them. We saw how you modulate, we saw how you demodulate, and what is the spectral footprint of the modulated signal. How much does it occupy in the frequency domain? One big piece that is missing is what happens when these systems are operating in the presence of the noise. This is what is kind of the limiting factor in all communication systems. You are always, sooner or later, your signal attenuates and it will actually hit the noise floor and start operating in the presence of the noise. And what we need to do is now go back to all of our modulations and evaluate their performance in the presence of the noise. Now to do that, we need some additional math, right? The noise, it turns out, is a random process, which is a signal that we can only characterize statistically. And what I'm going to do over the next couple of lectures is cover some basic mathematical tools that we need to characterize noise in a statistical sense. We need to review two major things. One is random variables. What is a random variable and how do we describe random variable in mathematical terms? And then the second thing that I want to review is random process, which is higher level than random variable. It's a random variable with a dimension of time where the noise is actually a random process. And then the third thing we have to understand, what happens when you present the random process to the linear system, because that's what we're dealing with here. So, kind of three parts here. First, I'm going to talk about random variables, then I'm going to talk about random processes, and then the third, I'm going to talk about what happens when you present the random process to a linear system. So, I guess let's first talk about random variables. So, what is a random variable? I'm going to use just this acronym, random variable, to minimize writing on the board. Is a single valued function that assigns a number that is an outcome of an experiment. Now, that's really not the clearest of all definitions. There's this notion of experiment, and we need to define it precisely. But I'm going to rely on our common understanding what these are. For example, what is an experiment? I pick, let's say, ruler and I measure the height of everybody here. So the experiment is measuring the height. The random variable is the actual height, the number that I attach to every one of the experiments. So we're going to have kind of pictorially something that we're going to call sample space, which is all possible outcomes of a given experiment. We're going to have outcome here, single measurement of some sort, or whatever, flipping the coin or whatever is the outcome of an experiment. And then we're going to have a function that is going to map this experiment to a real x. So it's going to assign a number to that outcome of an experiment. This function here is random variable, right? It's I attach a number to every one of the outcomes of this experiment. I call this x of lambda in my notes, and this outcome here is lambda. That's the outcome of the experiment. Now, how do we describe this random variable? There are some functions that we attach to this random variable that characterizes it in a statistical sense. So let me review those functions. So first function that we're going to be talking about is probability distribution function. probability distribution function. Another way to call this one is called is cumulative distribution function. Or CDF. Okay? So what is that? That's a function that we're going to attach to the random variable. If I say random variable height, then there will be some function that travels along that explains this random variable. So, so if x is a random variable, then CDF for x is defined as, so this is the notation, CDF of the random variable x evaluated at some point x0 is probability that x is going to take a value that's smaller or equal to x0. So going back to my example of measuring heights, so CDF of, let's say, 180 centimeters is the probability that whoever I measure here is going to be below 180 centimeters tall, right? So for every given value x0, I can attach the probability. Let me test you understand. If I say x0 is 3 meters, what's the probability that the measurement height is going to be below 3 meters? 1, right? Everybody is smaller than 3 meters. And if I say x0 is half a meter, chances are everybody is greater than. So probability that you're going to be smaller than half a meter is 0. Probability that you're going to be smaller than 3 meters is 1. So CDF is always between 0 and 1. It's a probability, right? It gives you a probability that the random variable is going to take the value that is smaller than whatever is the argument that you give to this function, right? This x0. How do these CDFs look like? Typical CDF would look like somewhat like this. This is going to be x, this is going to be CDF. It's always going to saturate at 1. And this is CDF of x, CDF of x. And then if I fix a point here, x0, the value here is going to be CDF at that point x0. And what does that give me? That gives me a probability that the random variable is going to take a value that is smaller than this given x0. There are some properties of CDF. Of cumulative distribution function. Let me just, a lot of them, they can all be proved in a strict sense from this definition, but they're all very, very easy to understand, just thinking about what CDF represents, right? So first property is that 0 is always smaller than CDF x0, always smaller than equal to 1 for every x0. And that's because CDF is a probability, and we define the probability as being between 0 and 1. So CDF takes the values between 0 and 1. It's a non-negative function, and it's also limited by 1. The second property is CDF of plus infinity is equal to 1. And the third property is CDF x of minus infinity is equal to 0. Now these are a little bit loose notations. The more appropriate way to write this would be limit when x goes to infinity, CDF x of x is equal to 1. But we kind of shorthand this. And the way how we understand this, probability that the random variable is going to take the value that is smaller than plus infinity is certain event, right? It has to take a value, therefore it is always going to be smaller than the largest possible value, which is plus infinity. Probability that it's going to take the value smaller than the smallest possible number is 0. It cannot be smaller than negative infinity. So it is always going to be bounded between 0 and 1. The fourth property of the CDF is that probability that A is smaller than X, smaller equal than B, is going to be CDF X evaluated in B minus CDF X evaluated of A. So probability that your random variable is going to take the value from an interval between A and B is going to be probability that you're smaller than B minus probability that you're smaller than A, right? If you are in between, if you are smaller than B but not smaller than A, then you have to be between A and B. There's no other solution there, no other option. Phi is that probability that you're going to take the value greater than A is going to be 1 minus CDF X over A. And that's also self-explanatory, because probability that you're going to be greater than something is 1 minus probability that you're smaller than something, and the probability that you're smaller than something is, by the definition, CDF of that something. Right? So that all of these are straightforward properties that are very useful. You kind of need to know them by heart, but they're all very easy to understand from what the definition of the CDF is. So let me give you an example of a CDF, and let's test a little bit our calculation. Example 1. So I have a random variable x that has CDF of x given as 1 minus e to the minus 2x for x greater than 0. So that's our, and I guess I can put here 0 for x smaller than 0. So that's my CDF of x. And the question is determine, first question, probability that x is smaller than 3. And the second question is probability that x is in the interval between 1 and 3. Okay. So how do I determine the first one? Probability that x is smaller than 3 is essentially, by definition, CDF of 3, which is 1 minus e to the minus 2 times 3, which is given as, when you evaluate this, is 0.9975. And then the second one is probability that x is between 1 and 3 is equal to CDF of 3 minus CDF of 1, which in our case is 1 minus e to the minus 2 times 3. That's CDF of 3 minus CDF of 1 is 1 minus e to the minus 2 times 1. And when you punch this into calculator, you can get 0.1329. Right? So now you can see how powerful this insight is. You know, it doesn't really tell me what the value of the random variable is at any particular point, but it kind of helps me bound, you know, what this random variable sort of what can it do, right? If I'm to dimension this system, let's say this x is some sort of voltage, and I want to understand I want to dimension the system, saying, well, what voltages I could handle. If I handle everything between 0 and 3, 99% of the time my system is going to be able to handle this signal, or this random variable, right? There will be less than 1% of the time, 0.25% of the time, where the signal is going to be outside of the bound. And then I have to kind of see, well, what happens in that case and so on. But this allows us to kind of make an engineering decisions on a basis of probability. And in practice, that's always the case. Right? We always dimension our systems to handle whatever they need to handle with certain reliability, with certain probabilities, and so on. So that's the first function that we're going to use, CDF. The second function that we're going to use to characterize random variable is probability density function, or PDF. Probability density. So PDF, this one is shortened as PDF. So PDF is defined in the following manner. PDF of x at the function x0 is derivative of CDF of x with respect to x when x is equal to x0. So what is the PDF? It's derivative of CDF, right? So and then what is CDF? It's a primitive function or integral of the PDF, right? These two are related through differentiation. How does PDF look like? If this is x, PDF of x might look somewhat like this, right? And what the difference here, major difference is that in the case of a CDF, we were able to attach physical meaning to every point on a CDF. The CDF at the given point x0 was a probability, right? It had a distinct physical meaning. Here, the distinct physical meaning is the area under the curve, right? And I'm going to talk in just a second what this means, this area under the curve. But let's look at some of the properties of the PDF. And then one of them will be, what is this area under the curve of the PDF? First, so some properties. First property is PDF of x is always greater than 0 for every x. It's a probability density, so it's always positive. Also, you can think of this in a different way. CDF of x has to be monotonically non-decreasing, right? It has to be CDF of a larger number is always larger than CDF of a smaller number, right? Think about what does it mean physically. Probability that you're going to be smaller than a larger number is always going to be larger than the probability of being smaller than the smaller number, right? If I say probability of being smaller than 7 feet, that's always going to be a larger number than probability of being smaller than 6 feet, because there will be some people in between, right? So CDF is always increasing, right? And then as a result, the derivative of the function that is always increasing has to be positive, right? The slope of that function is always positive. So PDF is always positive. The second thing is PDF, I should say something like this. Integral from minus infinity to plus infinity, PDF of x dx is equal to 1, right? The area under the curve of the PDF is equal to 1. This one is called normalization property. Let me defer the explanation of this one for just a few seconds here. The third property is CDF of A is equal to integral when x goes from minus infinity to A, PDF of x dx, right? This property here is actually the same as the definition of the CDF, of the PDF. PDF is the derivative of the CDF, therefore CDF is the primitive function of the PDF, right? You get to CDF by integrating the PDF. Now, What does this mean physically? This physically means what is the probability that your random variable is going to take a value that is smaller than a. So that's an integral between minus infinity to a. So now look at this previous one. What is a in this case? It's plus infinity. So what is CDF of plus infinity? That's probability that you're going to be smaller than plus infinity. What's that probability?
It's 1.
1. So that's why this is equal to 1. The area under the curve of the PDF is always equal to 1, right? It has to be. Now, because that tells you the probability that x is going to take value anywhere from minus infinity to plus infinity, which is always 1.
Yeah, would it be more logical to start PDF from 0 since the way the graph, to start the CDF from 0 since the way the graph of CDF looks like, between CDF A of negative infinity and positive infinity?
CDF exists for numbers smaller than 0, right? In general case, it can cover any x, right? 0 is just, there's nothing special about 0. We have, in this example here, heights. 0 is special because nobody is negative height, right? But if x is, let's say, some sort of voltage, then it can have, let's say AC voltage. It can take positive values, negative values. And you can talk in terms of what is the probability that x is going to take the value smaller than half a volt, minus half a volt, minus 100, right? There's, in general case, x can take value across the entire real axis. There's no, 0 is not special there. In some examples it is, right? Like in the height example, but in general case it's not. So this is it's kind of like what I drew here. This can be 0 and you can be taking values below 0 as well. And then the last one is the most important one, property. It's that probability, because this is what we're always going to be working on. Probability that a is smaller than x, smaller than b, is going to be integral from a to b, PDF of x dx. So the probability that the random variable is going to take a value within a certain interval from a to b is the area under the curve of your PDF function across that particular interval. So here's what I promised you earlier. This interpretation of this area under the curve is this. This is a probability that a is smaller than x, smaller than b. Okay? So that's the physical meaning of the PDF. So we do attach some physical significance. It's a probability density. But much clearer understanding of what PDF is when you look at the area under the curve. Area between A and B is a probability that you're going to take the value between A and B. That's why the area from minus infinity to plus infinity is equal to 1. Because the area the probability that you're going to be anywhere in this interval is a sure event. Right? You have to take one value, so the probability that that value is going to be between minus infinity and plus infinity is equal to 1. Okay, so those are the definitions of the PDF. Let's take a look at the example. It says find the PDF for the CDF in the example 1. Over there we had CDF of x being equal to 1 minus e to the minus 2x for x greater than 0 and 0 otherwise. So PDF of x in this case is derivative of this, so this is 2 times e to the minus 2x for x greater than 0 and 0 otherwise. So the PDF in this case looks somewhat like this. This is PDF of x after x goes like this when x is positive, before x it is 0. So this is PDF of x in the previous example that kind of travels with the CDF of x. Now, if you have one, you know the other, right? There is no any loss of information by knowing either PDF or CDF, right? They're related one to one. So theoretically speaking, it is irrelevant which one you have, right? you can work with CDF, you can work PDF. Practically, we find out that PDF is much more convenient because of the expectation operator. So most of the time when we talk about the random variable, we give their PDFs. You can say normal PDF, exponential PDF, binomial PDF, uniform PDF. So all of these are different PDFs that we work with as well. I mean, there's a normal CDF and exponential CDF and so on, but they are not used as much as PDFs, right? So most of the time we're going to be relying on a PDF, but you have to understand that either one of them is fine, right? Both of them are giving you the same type of information. Next thing I want to define here is expectations and moments. And moments. So consider now we have x is a random variable. Now we have f of x is a function of the random variable x, right? So x is just a number, so I can feed that number to a function, and what will come out is another number, right? And that number is also going to be random variable, f of x, which I can now determine its PDF, its CDF, and so on. Now, what is of special interest for us is expected value of f of x. So if I have x is a random variable and f of x is some function of the random variable, what is of a special interest to me is something that we use this symbol here, the expected value of f of x. And this is defined as integral when x goes from minus infinity to plus infinity, f of x times PDF of x dx, right? So what is the expected value of the function of the random variable? You take this integral here, you put f of x, then you put the PDF of x dx, and you integrate over all possible values for x. So that's how I determine the expected value of the function f of x. Now this works always. F of x can be any function. I can take what is the expected value of sine of x, put sine of x, PDF of x, crank the integral, I get it, right? But there are some f of x's which are special and that we're going to be dealing all the time with. So let's look at some special cases. For f of x. First special case is f of x is equal to x, right? I have a function to which I give x and it gives me back x, right? So what is the expected value of that function? Expected value of f of x in this case, or expected value of x, is going to be integral when x goes from minus infinity to plus infinity, x times PDF of x dx. And this is what we call mean value of x, or expected value of x, because now we're evaluating what is the expected value of x. So this is what we call mean. A lot of times we use symbol mu to indicate this mean, right? So how do I calculate mean? I need to know what the PDF of the random variable is. I put x here times PDF of x, and I perform the integration, and I get the average value or the mean value. The second one, also of a great importance to us, f of x is equal to x squared. So we have expected value of x squared, the same story. X goes from minus infinity to plus infinity, x squared times PDF of x dx. This is what we call second moment, right? Of the random variable. The third one of the great importance to us when f of x is equal in general x to the power of n. So this is expected value of x to the n, which you guess it's x minus infinity to plus infinity, x to the n, PDF of x dx. And this is nth moment. Right, so just a generalization of the number 2 here. The fourth function that is also of a great importance to us is f of x is equal x minus mu to the n. Right? That's you take the random variable, you subtract its mean, and you take the expected value of that. So this is expected value of x minus mu to the n is an integral when x goes from minus infinity to plus infinity, x minus mu to the power of n, PDF of x dx. How do we call this one? N central moment. Why is it central? Because it's centered around mu, around the mean. Right? Out of all central moments, there are some of them that are famous. Right? And what for n equal 2, you get the expected value of x minus mu squared. We usually designate this as sigma squared, and we call this variance. And then square root of variance we call sigma, or we call it standard deviation. Okay? So what is the standard deviation? It's the square root of the second central moment of the random variable. What is variance? Second central moment. Right? It's a second moment, but around mean. Here, let me ask you this. If mu is equal to 0, what's the relationship between second moment and second central moment? They are the same. Beautiful, right? For the 0 mean random variables, your second central moment and the second moment are the same. Why? Because when this mu is equal to 0, then you can see, as a matter of fact, that's the true for every moment, right, of the 0 mean variable. Because when mu is equal to 0, you can see that these two are the same. And now, these moments are used all the time. We always talk about mean, we talk about standard deviation. When you talk about mean, you're talking about so-called measure of the central tendency. You're saying, okay, on average, this is 5, meaning you're scattered around the 5, but the trend is there. The central tendency is 5. So when we talk about random variable, we typically talk about measures of central tendency, mean being the one that is used most commonly. And then the second piece of information that we always try to supply is how much of a scatter does the random variable exhibit around this central tendency. And then we talk usually in terms of standard deviation or confidence interval or variance. All of these are some metrics of how much is the variability. So you can say, for example, people in this room are 5 feet 10 with some standard deviation of, let's say, 5 inches, right? So you know kind of central tendency, and then what is the scatter around the central tendency. And that's kind of general way how we treat these moments. So let's look at an example here, how you evaluate the central moments for this case, or the one that we've been dealing with so far. So this is example 3. Says find the mean and standard deviation for the example 1 and 2. So here I have PDF of x given as 2e to the minus 2x for x greater equal to 0, 0 for x smaller than 0. It says find the mean and standard deviation. So let's first find mean. Mean is expected value of x, which is, by our definition, x goes from minus infinity to plus infinity, x times PDF of x dx. Right, that's no thinking involved here. This is what expected value means. Now, in our particular case, there is no need to integrate from minus infinity because the PDF is 0 whenever x is smaller than 0. So I can integrate from 0 to plus infinity, x times PDF of x. But PDF of x is 2e to the minus 2x dx. Okay? And the way how I'm going to integrate this is I'm going to say this is integral. When x goes from 0 to plus infinity, I'm going to put 1/2 outside and have 2x e to the minus 2x d 2x. Right? You see what I did? I just multiplied and divided by 2. Now, this integral here is equal to 1, so this is 1/2. Just a side note, let me give you, this is a table integral that comes really handy. So let me call this I n. Is integral from 0 to plus infinity, x to the n, e to the minus x dx. What is the value of integral? Anybody? N factorial. Right? So this is a integral that comes really handy because we end up integrating exponentials quite often. So this is what I applied here. If you look at 2x is a new variable, so I have x to the 1, e to the minus x dx. 1 factorial is 1, so the value of this integral is 1. And then this 1/2 was there because I had to multiply here 2x x by 2 and then divide by 2. Now let's take a look at standard deviation. Let's use this side of the board. So the standard deviation, I'm going to calculate first the variance. Sigma squared is expected value of x minus mu squared. So this becomes integral when x goes from minus infinity to plus infinity, x minus mu squared, PDF of x dx. So in our case here, this becomes an integral when x goes from 0 to plus infinity, x minus mu squared into the, I guess 2 times e to the minus 2x dx. Let me actually do it differently so that we do this slightly differently. So I'm going to continue with general case. I'm not going to worry about what this is in this particular case. Let me carry this a little bit longer before I substitute the actual values for this. So this is x goes from minus infinity to plus infinity, x squared minus 2x mu plus mu squared PDF of x dx. Still general case, this is always true. So now I have here integral when x goes from minus infinity to plus infinity, x squared PDF of x dx. That's the first integral here, just this x squared times PDF, right? Minus 2 times mu. Mu is a number, right? So it's not a variable, it's a constant, so you can get out of the integral, right? So I have 2 mu integral when x goes from minus infinity to plus infinity, x times PDF of x dx. And the last one is going to be plus mu squared, integral when x goes from minus infinity to plus infinity, PDF of x dx. This can be simplified. What is the first one? It's the expected value of x squared, right? If you look at it, it's a second moment, right? So this is expected value of x squared. Now minus 2 mu, what is this? First moment, right? Or mu, right? You see that? This thing, integral from x goes to minus infinity x to plus infinity x times pdf dx is mu, right? So I have here minus 2 mu squared, and then plus mu squared. Now what is this? What is the integral from x goes from minus infinity? 1, area under the curve. So you end up with a expression here that says that the variance is the difference between the second moment and the first moment squared. And this, I remember when I was sitting where you are, I would always have to think, is this true always, or there's some restrictions when this applies? It's true always, right? So you can calculate the variance by looking at what is the value of the second moment minus the first moment squared. Always true. So let's apply that in this particular case. I already have calculated mu squared. So let me calculate the second moment. So the expected value of x squared is, in this case now, is going to be equal, x goes from 0 to plus infinity, x squared times 2 e to the minus 2x dx. And I'm going to do the same thing as I did with the previous case. I'm going to say this is x from 0 to plus infinity, 2x squared e to the minus 2x d2x. And what do I need to put here to equalize everything? I have 2 squared, 4 from here, times 2, it's 8, but I have only 2, so I need to divide by 4. See that? So this is 1 over 4. Now what is the value of this integral? No, this integral. Look at this and look at this. If I imagine 2x as a new variable, 2 factorial, which is 2, right? So 2 factorial is 2, so this is 1 over 2. Okay? So now, my variance is going to be expected value of x squared minus mu squared, which is going to be 1/2 minus mu is also 1/2, so it's going to be 1 over 2 squared, which ends up being 1 over 4, and it's 1 over 4, and the standard deviation, which is square root of the variance, is 1/2. So this random variable happens to have the mean, which is 1/2, and standard deviation, which is 1/2. These are exponential variables. They are known for that property. If you have a random variable that has the property where mean and standard deviations are the same, the first thing you suspect that this is an exponentially distributed random variable.
I have a quick question, sir. Why did you choose to integrate with respect to all values of x for standard deviation?
Here,
Yeah, for x.
well, this is general case. I haven't really considered the problem, task at hand until I got here.
Okay.
So this is, I did this because I want you to remember this. This is equal to that. In general case, it is always true, right? And then I apply this in this particular case later on. But these steps here hold always. Because if you look at them, I've never assumed anything about any restrictions here. It's a general case conclusion. There are some PDFs that are more common than the other ones in a given area of application of this theory. The one that is so common in our area is the one, I guess it has its name, normal. right? Not the other ones are abnormal. This one just happens to be called normal or Gaussian. It should have been probably called common or frequent or something, but we call it a normal PDF. So normal or Gaussian PDF, so let me give you that one. /Gaussian PDF has this form. We say that X is distributed using a normal distribution with two parameters, mu and sigma. This is how we say that X is normally distributed random variable. That's the notation we're going to use. The normal distribution, and you've heard people call it also bell curve sometimes, looks somewhat like this. The mu is here, and then the width here is proportional to sigma. The analytical form of this distribution, normal distribution of mu and sigma, is given as 1 over square root of 2 pi times sigma into the minus x minus mu, everything squared over 2 sigma squared for every x. So that's the format of this distribution. Now it can be really easily shown that the expected value of x is equal to mu, and the expected value of x minus mu squared is equal to sigma squared. So these two parameters have also physical meanings. Mu is the mean value of the random variable, so it's a central tendency, and that's why this graph is kind of central around this mu. And the sigma is the measure of variability, measure of the scatter for the random variable, so it kind of tells you how wide distribution is, how often you have points far away from the mu. And I suggest you try this. Try to derive. There are some integrals that will show up. They're not as trivial, but they're not hard to do. Now, why do we call this normal distribution? It appears very frequently in a phenomenon that we're trying to treat in communications and in general. It turns out there is something called central limit theorem. And there's a formal statement of the theorem, and I can state it, but in this course we don't have time to prove it. What I would like you to understand is this. It turns out if you have a random variable that depends somehow on many phenomena underneath, then it tends to be normally distributed. Let's go back to my example from the beginning of the class where I measured the height of people in this classroom. Right? You kind of intuitively sense that there are a lot of things that determine someone's height, right? Genetics, race, nutrition, whatever. There's whether they are into sports or whether they're into video games or whatever, right? So all of that ends up in one number that we call height. There are a lot of these phenomena that kind of participate aggregately in determining what this random variable ends up being. So the height, if you look at height in people, it tends to be normally distributed, right? And whenever you can kind of see that the random variable has no dominant component to it, something that makes it go one way or the other, then it tends to be distributed normally. And that's quite frequently the case in a lot of practical examples. Okay, any questions of anything so far? So far we've been talking about one-dimensional phenomena. This is this function, single-valued function, that takes an experiment and gives it a single value. Now, what we need to look at next is random processes. processes are very important for us because most of the signals that we really care about fall into that category. Earlier in the class, I kind of mentioned that even though we know how to determine, you know, the Fourier transform or Fourier series for periodic signal, or even Fourier transforms of the deterministic signals, that's of a limited use for us because we don't tend to send periodic signals or deterministic signals, because if I would like to communicate sinusoidal to you, there's no point in sending, let's say, 3 hours of a sinusoidal. I say, hey, here's a sinusoidal, its frequency is this, its magnitude is this, its phase is this. And that's it. You are able to regenerate that sinusoidal at the receiver, right? The same is with any deterministic signal. I send you a formula and then you can determine what the signal looks like. So what we are really sending through our communication systems are random processes. We're sending signals that you don't know a priori what they're going to be. There's no point, or there's very little point in calling somebody if you know exactly what they're going to say, right? So you're actually calling them, and then what you get out of the call is the randomness of what they're saying, right? What is the information that is in the random part of what they're saying. So of particular interest to us are random processes. That's what we are sending through our systems. So we need to understand, how do we characterize random process? So we have an experimental space. So this is our sample space. This is one of the outcomes, and we call this outcome lambda. But now, the random process does not attach a single number to the outcome, but instead it attaches this function of time. So this is why x, let's say lambda of t, right? So that's an outcome lambda. Let's call this lambda 1, and this is an outcome x1. So as a result of this experiment, let's say I call somebody, they start talking, and I look at what they've been saying. That's a random process that is a function of time, right? I call somebody else, they give me yet another process. They give me another function of time that might look somewhat like this. Xn of t, and so on. The way how the easiest way to understand what a random process is the random variable that evolves through time. That's an easy way to picture this. So if I freeze time, and that's how we're going to be analyzing all of this. So if I set t equal to t0, every one of these functions of time will have a single value. So at any given time, I'm going to have distribution of these values and associated PDF, CDF, and so on. So I will have a random variable. But that random variable changes through time, right? So we have two dimensions here that we are dealing with. One is the amplitude dimension, where I have a random variable. And when I characterize the random process, I have to tell, what does this process look like in the amplitude domain? What is its mean? What is its standard deviation? What is its PDF, CDF, whatever I use to characterize the process in the amplitude domain. But that's not enough. What I need to also explain is, how does this process evolve over time? So I need to have another descriptor that tells me, how does this process behave along the t-axis? From our background, the best descriptor that I can possibly have is, what frequencies or what sinusoidals do I need to build this process, which we're going to call the power spectral density of the process. Alternative to that is something that we call autocorrelation function. But what I want you to understand at this time is, there are two qualities that we have two kinds of descriptors that we need to describe the random process. For every random process, for example, voice, I need to tell what is the amplitude behavior of the process. You know, how does it behave if I freeze time? And then the second thing that I need to describe is what is the time domain description of this process? How does this process evolve over time? So while random variable, we had one type of the descriptor, PDF or CDF. Here we're going to have two kinds of descriptors, PDF and CDF in the amplitude plane, and autocorrelation function or power spectral density along the t-axis. So let me just put that here. So there are two types of descriptors that are needed for characterization of random process. One is the amplitude domain, which is CDF, PDF, and so on. And the other one is time domain, which is autocorrelation function power spectral density, and so on. So I need two things. So let me go back to amplitude, right? Just to clarify. So at any given time, t equal t0, you can see that all of these random processes that are attached to all possible outcomes of the experiment will take a single value, right? So I can say all of these values, and there is infinitely many of them. So at any given time, t equal t0, random process is fully characterized with its PDF. So you can say something like this: x of t when t equals to t0 is some PDF of x when t is equal to t0. So at any given, let's say here, time, I can imagine that there is some probability density function, PDF of x at this time t equal to t0. Okay. Now, with respect to how this PDF can change over time, or doesn't have to change over time, based on whether this PDF changes over time or it doesn't, we have two classes of the process, of the random processes. If PDF of x t equal t0 does not depend on t0, we call this process is stationary in amplitude domain. So what is the process that's stationary in amplitude domain? You look at all of these realizations of the process, you freeze the time, and you look at the distributions of the amplitudes, and that gives you some histogram or some PDF. Now you do that, wherever you do that along the t-axis, you find out you're going to get the same distribution. That process we call stationary. It statistically, it does not change in the amplitude domain over time, right? regardless of where I freeze time, statistically it's the same process. The actual values are going to be different, right? So you see here, if I look at across one realization at two different times, the value is going to be different, and that's fine. But if I look at the distribution across all possible realizations at two different times, I get the same PDF. So the process is stationary. It does not change its statistical properties over time, right? A flip side to this is if PDF changes, PDF of X changes as a function of T0, the process is non-stationary. Okay? So these are two big classes. Now it turns out we have one important class of processes that are non-stationary, strictly speaking, but they are stationary in a wider sense. So let me explain what that means. We define the third category if mean and variance of a process does not change over time. We call this process is wide sense stationary in amplitude domain. So we have kind of black, white, and gray, right? Black is, in this case, the process is stationary, meaning its PDF, entire PDF, does not change over time. Okay? The process is non-stationary if anything changes. Like in general, PDF, if the PDF changes over time, the process is non-stationary. Now, if the PDF changes over time, but the mu and standard deviation does not change, or mu and sigma squared does not change, the first two moments stay the same, we call that process stationary in wide sense of the word. Meaning its average value does not change, and its power does not change. The statistics may change somewhat, but these first two moments don't. And that process we call wide sense stationary. So, three things. Stationary, and since we are looking at the amplitude domain so far, all of these conditions are for amplitude domain only. Right? Process can be, for example, I'll talk about it in just a second, but we're talking now stationarity in the amplitude domain. We're going to define stationarity in the time domain, and then we're going to say if the process is stationary in the amplitude and in the time domain, it's stationary altogether, right? And these are going to be really, really nice processes that turns out, although it seems like a lot is required for that, it turns out that the one that we care the most about, which is noise, ends up being that kind of process. At least we can model it that way. So any questions about characterization in the amplitude domain? It's pretty straightforward. You're just looking the y-axis and you're examining what does this signal do along the y-axis. And then along the y-axis, the signal is essentially just a random variable that we attach the PDF to. And if that PDF changes over time, then the signal is non-stationary. If it stays the same, the signal is stationary. Now let me first, before I go and talk about characterization in the time domain, let me illustrate why do we need that characterization? Because although I stated it, I'm not sure that I solved it properly, right? That you're still believing, right? So let me show you two processes that have the same behavior along the y-axis but they're completely different along the t-axis, right? So, so the random process or random processes may have same behavior along amplitude axis but different behavior in time. So let me draw two signals. This is the first signal, and it looks somewhat like this. Right? So that's x1 of t. And where is the amplitude behavior? Is this distribution along this axis, right? You can think of, there is some, let's say, normal distribution that shows how does the signal behave in along y-axis. Now look at this signal. This signal, when you look at it in the amplitude domain, has the same sort of amplitude distributions as this one. It is occupying the same range, probably going through the same levels with the same frequency as this one. But what can you tell me about this signal? It's much more slower, right? This one is much more fast. So you have the same behavior along the y-axis. If I give you PDF, let's say in both cases it's normal PDF. But you can tell me that the frequency content of this one is much more rich than the frequency content of this one. That's the behavior along the time axis. So we need a way how we capture this. To say, yeah, these two have the same amplitude behavior, but this one is somehow different than this one in the time domain. So what we use to characterize the time domain behavior is something called autocorrelation function. So characterization of time domain. Behavior. So we define a function r of x, rx of t tau as expected value of x of t times x complex conjugate of t plus tau. Okay, so that's the definition of autocorrelation function. How should you understand it? Well, let's draw a couple of graphs here. So I have some random process. Here are the different realizations of this process. This is x1 of t, x2 of t, n of t, and so on. And I look at the value here. This is x of t. This here is x of t plus tau. x1 of t plus tau. So I form a product. x1 of t times x1 of t plus tau, and I complex conjugate that one. It's not important for real signals, but when signals are complex, then it starts playing a role. So I take this, I move tau away, and then I take the value of the signal there, and then I multiply that. And this is a new variable. Let me call this now y of t, or y of t tau, y1 of t tau. Now, I do same here, so I get x2 of t times x2 complex conjugate of t plus tau, and I call that y2 of t tau, and so on. xn of t times xn complex conjugate of t plus tau, and this is yn of t tau. Now, this is now a new variable that will have its own distribution, right? And then I'm looking at the expected value of this random variable. So in a sense, I'm looking at the expected value of y of t tau, which is integral over all possible y t tau times PDF y t tau dy. So PDF of y over all possible y. So I'm looking at the expected value of this guy. Just for the sake of completeness, finish this joint. Now, how does this capture the time domain behavior? Well, look at these two cases, and let's take a look at small tau. If I look at the small tau, in this case, the two values are going to be very much the same, right? For small tau, this signal is slow, so the values that are separated by small tau are very much the same. So this product is always going to be large, or it's at least going to be of the same size. Right? Now, if I look at this one, you know, even for small tau, this value has nothing to do with this one. We say, in this case, for small tau, the values are uncorrelated. They can be anything. But here, you know, for small tau, the values are correlated. So if I know the value of the function at this time, I can pretty much guess what happens, you know, a little bit away, right? So if I can guess, that means that I'm capturing some sort of time domain behavior, right? If my autocorrelation function is slowly moving, or it does not change rapidly as a function of tau, then my signal is slowly moving in time. We're going to go through this in more detail, but for right now, look at this function here, understand what it is. Now, we can now define based on the autocorrelation function, again, two classes of signal, right? We can say if this autocorrelation function does not depend on t, in other words, it only depends on tau, then the process is stationary, right? No matter where I start looking at the autocorrelation, I'm going to get the same values as a function of tau. The process is stationary. If the autocorrelation function changes as a function of t, the process is non-stationary. So you have, and we're talking about time domain now. So if r of t tau depends only on tau, the process is stationary in the time domain. So let me just summarize that. It's going to take me just a minute. So I have, again, black and white. I have r t rx t tau is equal to r of x of tau. Does not depend on t. That kind of process is stationary. The flip side is Rx stationary in time domain. If Rxt of tau depends on t, process is non-stationary. And then the final definition, if the process is stationary in both amplitude and time domain, it is stationary in the strict sense. All right. Any questions? Okay, let me give you some exercises. So it's 6:18, 6:19, 6:20, 6:21, 6:24, 6:25, and 6:29. Okay. When we come back next time, I'm gonna finish the random processes, and then we're gonna do a review for the returning cycles.